Alright, afternoon everyone, my name is Daniel Wieseneck. I will be presenting the results for the refrigeration cycle, which I completed with Brett Wilson and Ramon Weber for the ME4611 lab. On the left you can see was actually right there in this building, the actual experimental apparatus and setup, which I'll get into details later. So what we're going to go over, we're going to go over an introduction, some background theory, some of the formulas that are used in this lab for analysis, the procedure and the safety as a part of actually completing the lab, the apparatus and setup, the results, any outcomes and uncertainty along with that. So the goal of this experiment is to analyze the performance of a heat pump using the coefficient of performance. There are four main components in the refrigeration cycle. So the compressor, if you want to skip to the next slide. So the compressor is going to heat the fluid and give a hot pressure and hot temperature gas, which will then enter the condenser, where we have a warm pressure and low temperature liquid, which will then enter the expansion valve, which will be the low pressure and low temperature liquid and vapor. And then at that, we will enter the evaporator, which will then generate a low pressure and warm temperature gas, which will then repeat and go into the compressor. And to kind of give us a metric of how this works, the main thing is the coefficient of performance. This is a ratio used to compare the amount of cooling generated to the amount of electrical energy consumed by the compressor. And to the right, you can see the pressure versus enthalpy diagram for the different states, where we have the energy input at the compressor from 1 to 2, and then we have energy output at the condenser from 2 to 3, and then from 3 to 4 where the liquid is expanded, and then 4 to 1 where it evaporates and starts over. So as I said, the COP is the main metric used to analyze this experiment, and that is calculated as the heat divided by the work input. The work input is H2 minus H1, which is at the compressor, and the heat is the enthalpy of state 1 minus the enthalpy of state 4. And the COP of the system acting as a heat pump can also be found, and it is 1 plus the COP of the refrigeration cycle. So the apparatus and setup, as I said, the four main components are compression, condensation, expansion, and evaporation. But along with this, we will have two different water pumps. These water pumps will have two valves, which we will be using to throttle the flow, which is one of the main things that we will be looking at in this experiment. And there are sensors that will give us pressure, temperature, and flow indication, so make sure that we get the right data to use for analysis. So what is the procedure? First step is to turn on the TRCVC and to start the software. Once we have that, we want to set the compressor to 40% to make sure that we are not operating or damaging any of the components. We're going to let that system stabilize, and using the valves at the bottom pumps, we will be throttling the flow rate to set at 5 liters per minute, 3 liters per minute, 4.5 liters per minute, and 6 liters per minute to get different data points. So some safety, as usual, proper PE, make sure that there's no leak in the refrigerant, which we'll be using the data from, R134A, and to stay within the compressor percentage of 40%. Another one is to make sure that whenever you're throttling the valves, that you aren't doing it too fast or too slow, to make sure that your computer data indicators showing it properly. So some of the data and calculations, this is from our first test, where we had a 5 liter per minute. As you can see, the power is at 0.4 kilowatts, and we're able to produce a heat of 1.37 kilowatts, and the coefficient of performance was 3.46. It normally averages from 2 to 4, so it's a pretty good coefficient of performance. And what we used was the temperature at the inlet of the condenser, the outlet of the condenser, the inlet flow rate, which was a little bit above 5 liters per minute for us, and the power consumed. It's important to note that the flow was a little bit above 5 due to our inability to take it. So the data from the other three, where we had the 6 liters per minute, 4.5 liters per minute test, and the 3 liters per minute test, are shown below with the different pressures, which we'll also be using to find the enthalpy. If you want to go to the next slide, I have some sample calculations of how we actually found the enthalpy, which we interpolated from data sheets. And from that, this is for the 6 liters per minute test. We had a COP of 2.5, and it does, again, averages from 2 to 4, so that is a reasonable outcome. Next, these are the COPs for the different tests. As you can see, the coefficient of performance, that the refrigeration cycle reduced in performance as the flow rate was reduced as well. This is similar to other data from other experiments. I think kind of, if you want to go to the next slide, some of the possible sources of error that were covered in past presentations that similarly apply to our presentation is that the system may have not reached steady state. There may have been inaccuracies in the readings from the indicators, the flow meters or the temperature indicators, and maybe an inaccurate compressor power consumption, inaccurate expansion valve not working properly, and the pumps performing at different flow rates, because there are the two different pumps, may affect the flow rate of heat transfer within the condenser and the evaporator. So to conclude, I think we got a good understanding of the refrigeration cycle. Here you can actually see it on the temperature entropy diagram, which was less important for our application with the work in, and how we use the coefficient of performance to base a metric of the refrigeration cycle to deem it operable or well used. That's all. Thank you.